Some Hardy-Weinberg problems. We're going to keep two equations in mind. This first equation, p plus q equals 1, which is what will be used to calculate allele frequency or allele percentage. If I ask you for homozygous recessive or homozygous dominant percentages or frequency, you're going to use this p squared plus 2pq plus q squared equals 1. Same thing if I ask for percentage of heterozygous individuals or frequency of heterozygous individuals. Okay, so let's just jump into it. Oh yes, one more thing. If you can kind of keep this straight in your mind, P of the equation is going to be referring to dominant allele, where Q is going to refer to the recessive. So maybe one way to remember that is that P comes before Q in the alphabet, and maybe you can think of it as dominant tends to kind of override, quote unquote, or come before a recessive trait. So first question is, the frequency of two alleles in a gene pool is 0.19, that's represented by large A, and 0.81, which is represented by little a. So you already know the allele frequency of the dominant allele and the recessive allele. The dominant allele of 0.19 is also the same thing as saying 19%, and this is the same thing as saying 81%. Assuming that the population is in Hardy-Weinberg equilibrium, the first question is to calculate the percentage of heterozygous individuals in the population. So according to the Hardy-Weinberg equilibrium equation, heterozygotes are represented by the 2pq term. So right away, because it's asking for percentage of heterozygous individuals, you should be using this equation to answer this first question. So therefore, since heterozygotes are represented by this term, 2 times p times q, and we already know p and we already know q, you would simply just multiply 2 times 0.19 times 0.81, which gives you 0.3078, or it's the same thing as saying 31%. Moving to the next part of this. Calculate the percentage of homozygous recessives in the population. So again, it's already asking for a percentage of homozygous recessives, so you should be referring to this equation. And the part of the equation that refers to homozygous recessives, remember recessive allele is represented by Q. Where is Q here? Well, it says that Q should be squared. We already know the allele frequency for Q, which is 0.81. So Q squared, or 0.81 squared, is 0.6561, or the same thing as saying 66%. Okay. Number 2, an allele W, large W, capital W, which is the dominant representation. For white wool, it's dominant, and it's dominant over the little w allele for black wool. So in a sample of 900 sheep, it's telling you that 891 of them are white and 9 of them are black. So calculate the allelic frequencies within this population, assuming that the population is in Hardy-Weinberg equilibrium. So we know that the allelic frequency of W is represented by the Q term, and we know that large W is represented by the P term. So in order to calculate the value of Q, you have to get, first of all, the percentage of Q, of recessive, which is the black sheep, right? The black wool. So it's telling you that 9 out of 900 are black. So if you just divide that, that is 0.01, or the same thing as saying 1%. So hopefully that's clear, that 9 out of 900 have black wool, which means that 1% of the population have black wool. And you know that black wool is recessive. The only way to have this is to have little w as your genotype. So we know, now that we know the percentage, we know that this represents percentage. So 1%, or 0.01, is what Q squared equals. Q squared equals 0.01. So in order to get the allelic frequency of little w, we take the square root of 0.01, and you get 0.1. Now it's asking for the allelic frequencies within the population. So it's asking for the allelic frequencies. So this little w, which we just found out, but then also the dominant allele, large W. Since we know the frequency, the allelic frequency of the recessive allele now, we just have to use this number to plug it into our first equation, because this is the allele frequency equation. So if you just plug it back in here, we just found Q, and do your subtraction, 1 minus 0.1, and that will give you the value for P, which is 0.9, right? So that means that there is, as far as allelic frequency is concerned, there is 90% allelic frequency for the dominant allele, and there is 10% allelic frequency for the little w recessive allele. Okay, so number 3. So in a population that is in Hardy-Weinberg equilibrium, the frequency of the recessive homozygote genotype of a certain trait is 0.09. So this is where I was saying that frequency and percentage can be used synonymously. So all it's saying is that the percentage of homozygous recessive individuals, and it's tied to a particular trait, the trait doesn't matter in this case, is the percentage of homozygous recessive individuals is 0.09, or 9%. So it wants to know the percentage of individuals that are homozygous dominant or just homozygous dominant. So we know that the frequency of the recessive homozygote genotype is Q squared. And we also know that it's equal to 0.09. So if you just take 0.09 square root of 0.09, it will give you the allelic frequency for the recessive allele. Now we can use that in our P plus Q equals 1 equation to find the allelic frequency of the dominant allele. It's asking for the percentage of individuals that are homozygous dominant. In order to do that, we have to, again, recall that this is what we use to calculate percentages of the genotype, right, which is a combination of two alleles. Depending on the allele, if it's homozygous, it's obvious going to be two of the same allele. If it's dominant, hopefully it's clear, it's big letter, big letter. If it's recessive, little letter, little letter. Here is our dominant allele frequency. So in order to get a percentage of individuals that are homozygous dominant, you have to square it, and this gives you 0.49, or 49% of individuals are homozygous dominant. Next one. In a population that is in Hardy-Weinberg equilibrium, 38% of the individuals are recessive homozygotes for a certain trait. In a population size of 14,500, calculate the percentage of homozygous dominant individuals and heterozygous individuals. So it's starting out by saying always start with the homozygous recessive percentage if it's given. I think that this is not exactly true, but if it were to be true, this is maybe the reason, which is, if you've got a homozygous dominant population, and of course there's going to be some component of that population that's heterozygous, that dominant allele is going to exhibit that trait, even if you're heterozygous. The only way that the trait will be masked, or if we're talking about a disease here, if the recessive genotype is what displays the disease, the heterozygous will not. So in that case, you're not really getting a true, I think, number in terms of percentage when you're just looking or just dealing with the dominant value, if that's what you're given, because that's not really, that's going to be tied into the trait even if they're heterozygous, right? So if something is dominant, Clearly, it's going to show the trait if it's homozygous or if it's heterozygous. So I think that's why that they always recommend to start with the homozygous recessive percentage if it's given in the question. But that's just me kind of trying to like work that out or flesh that out in my head. I think that's why. That's neither here or there. So in this case, you are given the number for homozygous recessive percentage. And we know that because of the equation, the Hardy-Weinberg equation, we'll go back up here, that it is Q squared, right? So Q is recessive. Q squared is going to be the percentage of recessive individuals, genotype, homozygous recessive. This is the percentage of homozygous dominant, genotype. So we know the frequency of homozygous recessive individuals. It's 0.09, which is Q squared. In order to get the allelic frequency, we have to take the square root of that, which is 0.3. So, oops, I'm sorry. I started going over the same question. The percentage of individuals that are homozygous recessive is 38%, which is the same thing as 0.38. That is Q squared. You have to take the square root of that to find out what the allelic frequency is for the recessive allele, which is 0.616. So now we can plug this into our P plus Q equals 1 to find out what the allelic frequency of the dominant allele is, which is 0.384. So that's just allelic frequency now of the recessive and dominant alleles. In order to get a percentage that represents the homozygous dominant individuals, we have to square that, because remember, P squared is what tells you the percentage of homozygous dominant individuals. You square that value, you end up getting 0.147, which is the same thing as saying 14.7%. The last part of this is asking for the percentage of heterozygous individuals, and you can use the 2PQ term now to find that out. We found out already what our Q term allelic frequency is. We already found out our P term, or dominant allele frequency, so now we can just plug that in and multiply them to find out what the heterozygous percentage is in this population. If I were to ask you now to give me actually a number of individuals within the total population of 14,500, you would want to now use these numbers to give me actual individual or a head count. So if we know that 14.7 of the individuals are homozygous dominant, you would just multiply that, right? 14,500 times 0.147, and that would tell you that 14.7% in 14,500 people is 2,132 people, which are homozygous dominant. Same thing with the heterozygous. So if I ask you, like, okay, give me the percentage, but now tell me how many individuals is that, because there's a percentage of the group, but how many people is that within the group, then you would do the same thing. We already found out that 47.3% are heterozygotes, so you just multiply 14,500 times 0.473, and that gives you 6,859 people are heterozygous. And you can double check this work. You can just multiply. So if you just did the last bit of it, so we already knew from the beginning that 0.38 of the individuals were homozygous recessive. You can just do that last calculation to see how many individuals that is. And you should be able to add up these three numbers and get the total population number. This is a bit over, but that's just due to rounding. But that's fine. That tells us that we are doing these calculations correctly. So hopefully that's clear. And as I said, I will post more questions to give you more practice.